Roles taken care of. Let's run through that homework problem that stumps you guys so much real quick, and then we'll do graphical convolution. All right, so as soon as my laptop stops having a panic attack, any minute now. Homework number 2, problem 2. So in this problem, you were given the following circuit. Dot here. Dot here. These coils are coupled. Here's J omega M. There's I1. Minus J4 ohms. Here are our terminals for V out. Did I specify the directions of the currents, or did I let you choose them? All right, well then I'm going to choose this one and this one, just good plain old mesh currents. This is going to be the voltage drop across coil 1. This will be the voltage drop across coil 2. So the voltage drop across coil 1 should be J1 ohms times I1 plus J omega, omega M times, let's see, so the current is flowing into the not dot, so we should have a minus sign there. Let me think about this. Oh, no, I1 minus I2, sorry, brain fart. That looked okay for the voltage, induced voltage for V1. All right, for V2, we should have, let's see, so J1 ohms times I1 minus I2 plus J omega M times I1, right? That look okay? All right. So now I'm going to do KVL around the left-hand loop. So I'm going to have negative Vn plus 1 ohm times I1 plus V1 plus V2 is equal to 0. Let's expand this out a little bit. So I'm going to have Vn is equal to 1 ohms times I1 plus J1 ohms times I1 plus J omega M times I1 minus I2 plus J1 ohms times I1 minus I2 plus J omega M times I1. And now I'm going to simplify this a little bit. So let's see, what do I have here that's being multiplied by I1? So I have a factor of 1 ohms. And then I'm going to have an imaginary part. So I'm going to have a J1 from here and a J1 from here. I'm going to have a J omega M from here and a J omega M from here. So to me, that's going to look like 1 plus excuse me, 1 plus J2 times 1 plus omega m times I1. Now let's look at what we have going on for the I2 terms. So we have a minus J there is a 1 term from here, and then an omega m term from here. Like so. All right. So here's one relationship. Are we all okay with the algebra? Anything looking odd or terrible just yet? Anything not make sense? Okay. Now we're going to do KVL around the right-hand loop. Okay. So around the right-hand loop, we're going to have negative V2 plus 1 ohms times I2 plus negative J4 ohms times I2 is equal to 0. And now I'm going to just substitute things in yet again. So negative V2 is going to look like negative J1 ohms times I1 minus I2 minus J omega m times I1 plus 1 ohm times I2 plus negative J4 ohms times I2 is equal to 0. And I'm going to tidy things up. So let's see here. So for my I1 term, doesn't look like I have any real component, right? So I should just have negative J times, there's a 1 ohm term, and there's an omega m term. And then for my I2 term, I will have a real part. So that's going to look like 1 plus. Now let's pull our J's together. So let's see. Negative J1 times negative I2, that's going to look like a positive J1. So I'm going to have a J1 term from this. And then I have a minus J4 from this. So add those together and it looks like minus J3. So let me just swap the sign on this bad boy. Times I2 like so is equal to 0. Are we okay there? Anybody have any beef or anything? And so what I'm going to do now is I'm just going to rearrange this stuff to get I2 in terms of I1. Okay. So I can say that I2 is going to be equal to J times 1 plus omega m divided by 1 minus J3 times I1. And from this, I can now substitute this relationship for I2 into my relationship for Vn up here. And what I wind up getting is that Vn will be equal to 1 plus J2 times 1 plus omega m. What happens when I multiply minus J and positive J? So I'm multiplying this minus J right here and this positive J right here. What does that give me? Is it negative 1 or positive 1? Positive 1. All right. So I'm going to have a 1 plus omega m in the numerator and then another 1 plus omega m in the numerator. So it's going to look like 1 plus omega m squared. Sorry. Divided by 1 minus J3. Okay. So there's my relationship for Vn only in terms of I1. What is V out going to be? Negative J4 ohms times I2. By the way, if I have I1 right here, that be one of the different. Yeah, what the hell I was doing? Let me fix that. Sorry. Yeah. So V out is negative J4 ohms times I2. So that negative J here times this positive J here is going to look like 1. And so I'm just going to have 4 times 1 plus omega m over 1 minus J3 times I1. And let me just do this 4 ohms so the units work out correctly. Are we okay with this? All right. So now I'm going to take the ratio of V out to V in. So V out divided by V in is going to look like 4 ohms times 1 plus omega m over 1 minus J3 times I1 divided by 1 plus J2, 1 plus omega m plus 1 plus omega m quantity squared divided by 1 minus J3. We block this thing off here. All of this times I1. These I1s cancel each other. We okay with that? And now I'm going to multiply through by 1 minus J3 over 1 minus J3 to clear some fractions of it. Okay. That times there looks too much like a less than sign for me, so there we go. Okay. So what this is going to leave me with is 4 times 1 plus omega m divided by see here. 1 plus J2 times 1 plus omega m. This quantity will be multiplied by 1 minus J3 plus 1 plus omega m squared. And now I'm going to have to expand out the left-hand term in my denominator. So I'm just multiplying this 3 by this 1 minus J3. And so let's see what that's going to do for me. So let me put my numerator down. 1 plus omega m. So 1 times 1 is 1. 1 times minus J3 is minus J3. Then I'm going to have, so that's this times this, and then this times this. So now I need to multiply this J2 term, all that times 1. So plus J2, 1 plus omega m. And then I need to multiply that by J3. So let's see, J2 times negative J3 is going to look like plus 6, 1 plus omega m. Plus 1 plus omega m squared. My algebra okay here? Did I screw anything up? Any algebraic mistakes? Anybody notices anything? Okay. And so what I'm going to do now is lump things together as real and imaginary parts in my denominator. So this J2 times this minus J3 gives me positive 6 times that back up there. So this step is just me prettying things up. So 4 times 1 plus omega m in my numerator. And then I'm going to have 1 plus 6 times 1 plus omega m plus 1 plus omega m quantity squared is the real part of my denominator. For my imaginary part, so let's just call this plus j. I'm going to have twice 1 plus omega m hold on, let me double check this on something's. So 1 times 1 is 1. I got that part down pretty hard. Minus J3. Oh, no. I know what it is. Okay. Yeah. So just minus the 3 there. Okay. So this ratio has to equal 0.49 according to the problem statement, right? So let me ask you what is a really dumb question. Is 0.49 a real number or a complex number? It's a real number. So what's the only way that this ratio, which contains a complex number, is going to ever equal to just a real number? If the imaginary part goes to 0, right? So two times 1 plus omega m minus 3 must equal 0, which means 2 times 1 plus omega m must equal 3, or 1 plus omega m must equal the 3 halves, or omega m must equal the 1/2, right? Okay, so now we need to figure out k. Okay. So k is equal to m divided by the square root of L1 times L2. That's literally the definition of it. So I'm about to get real fancy here. I'm going to multiply my numerator by omega. And then I'm going to have omega L1 times omega L2. And I literally talked about this when we introduced the concept that you can use either the impedances or the specific component value here, right? So rearranging this guy, we're going to have, let's see, no, we don't have to rearrange anything, right? So that's just going to be one half over the square root of omega L1 is 1 ohms and omega L2 is also 1 ohm. So 1 times 1 is 1 half. So I told Nicholas this yesterday, and I'll give you guys fair warning as well. This level of algebra is going to happen a lot in your microelectronics class, just to give you a heads up. So I don't know, be prepared. It doesn't matter. 0.49 real. Right. All right. Any questions about this before we move on to graphical convolution? All right, graphical convolution it is. So the process of graphical convolution is very similar to convolution like we looked at on Wednesday. I don't know where the screen went. Except that we are going to use pictures to help in our understanding of what's going on. Okay. So I will explain the process of graphical convolution as we work a couple of the things. So stop crapping out. So let's say that I have the following two functions, right? So this is going to be f1 as a function of time. And let's use a simple unit step function for f1. So this is, our function has a value of 1 at t is equal to 0 and for all t greater than 0. And our second function that we're going to be looking at, I'm going to call it f2. And for this particular example, f2 is going to be piecewise function. So this is going to be 2. We're going to have an exponentially decaying thing here. So this is 2e to the negative t. And then let's have an exponentially increasing thing on this side. Draw this better. Like so, where it's going to hit its peak value here. Damn it. At -2, and this is characterized by the expression -2 e to the 2t. Okay. So we are going to apply the graphical convolution technique. We need to decide which of these two functions are going to be the one that we're going to flip around the vertical axis. So you want to flip f1 or f2? All right, so you guys chose f1, which is easier, so I'm going to do f2. So f1 will be easier. You're going to get the same result either way. Okay. So F1 of tau is just going to look like the exact same thing. F2 of tau, or actually we're looking at F2 of negative tau in this case, is going to be just this expression here, or this picture here, rotated about the horizontal, or excuse me, the vertical axis, right? So we're going to have something like this, where this looks like negative 2 e to the 2 times negative tau. We're going to have this bit right here, which looks like 2e to the positive tau. So now that we have some understanding of what's going on, we're going to talk about our process. Okay? So this is the one that we reversed in time. So it's the one that we're going to be sliding around in the graphical convolution process. So I like to start from effectively the negative side of the time axis and then slide to the right. Okay? So let's first look at what's going on when t is less than 0. So when t is less than 0, I'm going to start by drawing my function that isn't moving around. So that's my unit step function in blue. Sorry, and actually that should be tau, not t. And now, at some arbitrary value of t that is less than 0, I'm going to draw my function here. Now, for this particular case, where this function has value all the way from negative infinity out to positive infinity, it really doesn't matter where I'm choosing t to be for less than 0, and it won't particularly matter where I'm choosing t to be for greater than 0. But in other things, particularly causal functions and things like that, it'll actually make a lot more sense. Like you might have more than the 2 cases that we're going to deal with in this particular example. Okay. So this part right here represents negative 2 e to the 2 t minus tau. And this part over here is positive 2 e to the t minus tau. I'm just explicitly putting what these peak values are. Okay. So what I'm looking for is where these 2 functions overlap each other. Okay. So where do they overlap? Or what's interval? T greater than 0. Absolutely right. So for all time greater than 0, the product of these 2 functions is going to be non-zero. For all time less than 0, the product of these 2 functions is going to be 0 because of how our unit step function works, right? So for this interval, f1 of t convolved with f2 of t is going to look like the integral from 0 to infinity, because our overlap extends all the way from t is equal to 0 out to t is equal to infinity. My unit step function just looks like a 1. And now I'm going to have my -2 e to the 2 t minus tau, close that, d tau. So what can I do to this thing? Well, I can pull out that factor of -2, because that's a constant, and I can actually pull out a factor of e to the 2t as well, right? So I'm going to have -2 e to the 2t times the integral from 0 to infinity of e to the -2 tau d tau. Everybody okay with that? Yes, Ryder. Sure. So versus equals tau 0. Our unit step function has a value of 0. So my convolution integral equation, let me write the real equation up here, right? So y of t is the integral from -infinity to +infinity of f1 of tau times f2 of t minus tau d tau, right? So my integral here is going to be multiplying these two equations. So f1 of tau and f2 of t minus tau. I'm setting my limits of integration to be from 0 out to infinity, because I know that this part right here multiplied by this 0 is just going to look like a 0. This part right here multiplied by this 0 is just going to look like this 0. It's not until I get to t is equal to 0 and greater to where the product of f1 of tau and f2 of t minus tau actually has a non-zero value. Grace?
I have a question about how we this top right graph, this third graph, like on how we went from t to t minus tau, because one of the like curves is positive tau and one's negative tau.
So okay. So how did I go from here to here? Okay. So we are advancing this signal by some amount of t, right? We're shifting it to the left, which means we have -tau plus t, because we're shifting to the left. -tau plus t is the exact same thing as t minus tau. So effectively, well, when we did convolution on Wednesday, right, with just mathematical functions, to get our function as a function of t minus tau, we just replaced t here with t minus tau. We're doing the exact same thing. I'm just graphically showing you what's going on here when we flip it. When we slide it, it's going to look like t minus tau, and depending on what the value of t is, will either be to the left-hand side of the vertical axis or to the right-hand side of the vertical axis. But we're just sliding this thing around. And sliding it around involves adding or subtracting some arbitrary t. Does that make sense?
It was so when you say like replacing tau with like t minus tau, right?
Replacing t with t minus tau. So negative t, evaluating this function. So we have f2 of t here. f2 of tau would be the exact same thing, except tau would be on our horizontal axis. Like that's the units that we're moving. Negative tau means we're reversing it in time. So we're flipping it around the horizontal axis. And now as we advance for delay, we are adding some t to this. Okay, so any other questions before we get along with the calculus, which at this part is the easy part? Hannah, what's up? Right. So I'm just highlighting where these two functions overlap because that's telling me what the limits of my integration should be. Okay, so how do I perform the integral of e to the negative 2 tau? Negative 1/2. So negative 2 e to the 2t. Then we're going to have negative 1/2 e to the negative 2 tau evaluated at infinity and 0, right? So this negative 1/2 and this negative 2 cancel each other out. So that's just going to look like e to the 2t outside. And then I'm going to have, so what's e to the negative 2 tau at infinity going to look like? 0, right? Because e to the negative infinity is going to be 0. Minus, so what's e to the 0 going to look like? 1. So that's just going to look like negative e to the 2t. So this is what the convolution of these two functions looks like when t is less than 0. Okay. Now we need to consider the second case. Yes.
+1.
The negative 1/2 got multiplied by the negative 2, giving me a positive 1 here. So that's why it's a negative 1 in there. So it's 0 minus 1. So that negative 1 should go there. So now we're going to look at the second case. Which this is going to be for t greater than or equal to 0. I've just made a decision here because I'm not going to have enough time to work it both ways. So doing it the easy way is now going to be a homework problem for you guys, which means you'll have a place to check your answers. All right, so for t greater than 0, I'm going to draw my grid here. Here's my unit step function. Now, t is arbitrarily some positive value. So this is still going to look like 2e to the t minus tau. And this is going to look like negative 2e to the negative 2 t minus tau. And my overlap consists of all of this space. So realistically, here, I'm going to be integrating from 0 to infinity yet again. However, I need to break that integral up into two parts because the function that I'm writing it only has this value up to time equals t, and then it looks like this function for every tau greater than t, right? So y of t is going to look like the integral from 0 to t of 1, which is what my unit step function is contributing, multiplied by 2e to the t minus tau Did I miss a negative sign somewhere? That's what I thought, yeah. Let me double check things here. Yeah, you're absolutely right. So this should have had a negative sign there, and I just missed it. That's why I got it. All right, so let me just be really clear. 2e to the negative t is going to look like 2e to the negative t minus tau when I do that correctly. So thank you for that. d tau plus the integral from t to infinity of 1, the contribution of my unit step function, times negative 2e to the negative 2 t minus tau d tau. All right. So before we start messing around with this, are we clear where all of these terms came from? I apologize for my mistake on missing that negative sign on the graph of the part that didn't matter in the previous case. Yes, Ryder. Okay, so once again, going back to our fundamental definition, we're simply multiplying our first expression as a function of tau times our second expression as a function of t minus tau. So since our original expression here was 2e to the negative t, it should show up as 2e to the negative t minus tau when we're sliding it about. So at exactly t is equal to 0, it just looks like 2e to the positive tau. But realistically, this is negative t minus tau, where t is equal to 0. So it will be negative tau is positive tau. I probably actually should have written it as negative tau to remind me of what the hell I was doing, but that's on me. Okay. Hannah, what was your question? Same thing. Okay. All right. So any question about the limits of integration or anything here? All of that seemed fairly normal. James. Mm-hmm. Probably. Let's look at this thing here. Yes, it should. Damn it. So I'm just getting these mixed up. Okay. Yes, it definitely should be positive to t minus tau. Thank you. And I actually have it like that in my notes. I just wrote it down. So thank you very much, you guys, for paying attention and everything. Thank you, Brody. Get rid of that one there. All right. Any other mistakes that I've made for this setup part here? You guys are killing it. You're doing exactly what I need to do. Any other screw ups on my part? You're all, so let's go one at a time. Hey, what were you saying, I think?
The going up section of the graph on the right side.
Yes. Yep, okay. Negative sign goes here, just like I have in here, absolutely correct. Okay. Anything else? Daniel?
No, I'm looking. So where?
Understandably so, I'm looking like a real jackass today. Okay.
Like where the graph.
So are you talking about this region of space right here?
This red line goes through.
So over here, our unit step function looks like 0. So that's why everything to the left of the vertical axis doesn't have anything. For this bit right here, where we do have overlap from this and our unit step function, that is what this integral represents. So we're integrating from 0 to t to cover this bit, and then we're integrating from t out to infinity to cover this one.
Then the region above that unfaded after it passes through. That do that. I'm worried about that area.
Down here?
Above the line.
Oh, this one. Yeah, okay, let's shade it. Who cares? Yeah, that doesn't matter. Thank you. There you go. Anything else? All right. Okay, can we do calculus now, please? All right, great. So let's see. So we can pull the 2 out. We can pull a factor of e to the negative t out. So we're going to have 2e to the negative t integral from 0 to t of e to the tau d tau. Let's start here. Did I do this right? All right, I believe I did. Nobody's nitpicking things to death, so let's move along. Now I'm going to pull out a factor of negative 2e to the positive 2t, integrating from t to infinity of e to the negative 2 tau d tau. I believe I did that part correctly as well. All right. So that's going to look like 2e to the negative t times e to the t evaluated at t and 0 minus 2e to the positive 2t of negative 1/2 e to the negative 2 tau evaluated at infinity and t. So 2e to the negative t, that should have been a tau, e to the t minus 1 plus e to the 2t 0 minus e to the negative 2t. Any mistakes in that chain of math? Can't wait to be able to just do the little one. Yeah. All right, so anything wrong with this? I don't believe so. Okay, so 2e to the negative t times e to the positive t just looks like 2. 2e to the negative t times negative 1 looks like minus 2e to the negative t. Then I have plus e to the 2t times 0 looks like 0. E to the 2t times negative e to the negative 2t looks like minus 1. So that's just going to look like 1 minus 2e to the negative t. Putting these results together, we get negative e to the negative 2t for t less than 0, and 1 minus 2e to the negative t for t greater than or equal to 0. So that's what the convolution of those two functions are going to look. All right, let's work another one, and hopefully it's slightly less of a train wreck. Yes, sir.
Plot that out. That would be envelope of the graph.
Absolutely right. So if you convolve those two functions, you should get a function. So think about it from terms of one of them is the input and one of them is the impulse response of a system. If you put an input signal into a system, this convolution represents the output caused by that input signal. Yep, Hannah, what's up? Did I just remember it incorrectly? That should be positive. Yep. Nope. Just a typo on my behalf yet again. Sorry about that. Positive 2t. It's just this answer. Sorry about that. All right. Any other things that I've screwed up? Hopefully that clears up. All right. Let's burn through another one. So let's say that we have a function x of t that looks like this guy. So it has a value of 1 from t is equal to -1 out to t is equal to +1. And we have another unit step. Oh, actually, a ramp function. Scale on these is a little bit off, but it'll all work out. Let's call this one explicitly h of t this time. Okay. So which one are we going to flip? Yeah, let's flip x of t because it's the same thing if we flip it, right? So we don't have to do thought. And at this point, I need something where I don't have to put in a lot of thought, obviously. Okay. So x of negative tau is going to look literally identical. So here is -1, +1, 0. Okay. So let's convolve this bad boy. So what should my first case be? Okay, so let's think about it. I effectively want to set the limits of when these things are going to start overlapping each other. So unlike the prior problem, neither of these functions exist all the way from negative infinity out to positive infinity. So there's going to be some regions where we don't have any overlap, okay? So where should my, if I'm sliding this guy around, where should my region start? Okay. So if t is less than -1, let's look at that. So for any t less than -1, so here's tau. I'm going to draw this guy first because it's not moving. And here's t. Here's t minus 1. Here's t plus 1, right? So this is right before they start to overlap. This is the situation that I would have, right? So for any t that is less than -1, there is not going to be any overlap whatsoever because this guy goes over 1 unit, right? And so we won't have any overlap. So in this specific time interval, y of t is equal to 0 because there is literally no overlap whatsoever. Ryder, what's up? Yes. Yep, t minus 1 on the left-hand side, t plus 1 on the right-hand side. So let's think about what our next case is going to be, right? So I'm sliding this little rectangular pulse over to the right there, okay? So I think that I want to stop my next case before t hits +1, right? So when t is +1, which would be about right here, there's complete overlap between these two things. So there's going to be something happening before these two functions completely overlap. So for -1 is less than t is less than +1. I'm going to have something like this, where there is obviously some overlap. This is t minus 1 on this side and t plus 1 on this side. So what should y of t equal? What should my integral look like? What are the limits of my integration going to be? Let's start there. 0 to t plus 1. I agree with that. My unit step function, excuse me, is just going to look like 1. So I'll throw that a 1 in there. What about my ramp function? 1/3 t, or 1/3 tau, excuse me. Anybody have any problems with why this is the correct integral for this specific part of time?
Why
Yes.
didn't we go all the way in? The same function?
So if we go up to 3, so as we slide this thing past, we are going to have complete overlap. So we would be integrating from t minus 1 up to t plus 1. When we're in this space, though, so we're going to get to that point here in a moment. But when we're in this space, there is a region where when we multiply these two functions together, the result is 0. We need to take that into account. So how do I do this integration? What's the integral of t? T squared over 2, right? So the integral of tau would be tau squared over 2. So 1/3 times 1/2, I feel pretty strongly is 1/6. Okay. So 1/6 of tau squared evaluated at t plus 1 and 0. Correct me if I'm wrong here. It's just going to look like 1/6 times t plus 1 squared. Are we okay with this? Anybody got beef? I feel that level of math is where my brain is at for today. Okay. So now let's talk about the region that Brody was referring to, right? So for case number 3, let's talk about what happens when t is between 1 and 3. And then I don't think those matter, but just in case. Okay. So now functions completely overlap with each other. So what should my integral look like? All right. So from t minus 1 to t plus 1 of 1 times 1/3 tau d tau. Okay, I agree with that wholeheartedly. So that's going to look like 1/6 of tau squared evaluated at t plus 1 and t minus 1. So 1/6 of t plus 1 squared minus t minus 1 squared. Give myself some more room so we can expand this out. So t plus 1 squared looks like t squared plus 2t plus 1. T minus 1 squared looks like t squared minus 2t plus 1. This guy's going to cancel this guy. This guy's going to cancel this guy. And I am left with 4/6, so 2/3 t. Are we okay with that math? All right, now we have our next region. So it's effectively the other side of case number 2. So when the leading edge of our rectangular pulse goes beyond this ramp function. So this is going to be for 2 less than t less than 4. Here's my overlap. What am I going to have? T minus 1 to 3 of 1 times 1/3 tau d tau. Absolutely. So that's going to look like 1/6 tau squared evaluated at 3 and t minus 1. T squared minus 2t plus 1. So I'm going to pull out a negative sign, so negative 1/6. So t squared minus 2t minus 8. That's an 8. Nine minus 1, 8. And then when I pull a negative sign out, I wind up getting a negative. All right, and then my last region is for t greater than or equal to 4. Where they no longer overlap. And so y of t is equal to 0. Putting all of those results together, y of t will be 0 for t less than negative 1. It'll be 1/6 of t plus 1 squared for negative 1 less than t less than 1. It will be 2/3 t for 1 less than t less than 2. No, it should be 3, right? No, it should be 2. I'm sorry. So the reason why that should be 2 there, did I write that incorrectly up here? Yeah, that should be 2. Is because if we go out, so t is the midpoint of this thing, right? So if we allow it to go all the way out to 3, we have this area of overlap. So 2 is where that interval should stop. I apologize for that. And then negative 1/6 t squared minus 2t minus 8 for 2 less than t less than 4. And finally, 0 again for t greater than 4. All right. So, homework 2 is due tomorrow evening. Since I worked the hard problem for you, it should be fairly straightforward to get the rest of it. Homework 3, I posted yesterday, will be due on Monday. I'm going to post the homework set hopefully today, tomorrow at the latest, on convolution. That will be due next Wednesday, and then your exam will be due on Friday. Your convolution homework set will contain 4 problems. 2 will be like the convolution that we did on Wednesday, where I just give you functions and you do stuff with it. And 2 will be graphical convolution problems. Your first graphical convolution problem will literally be the first example that we worked, but I want you to specifically flip the unit step function as opposed to flipping the weird hyperbolic looking thing. Okay. All right. See you guys on Monday. So homework 2, the only answer I need to do is for the last problem. So I just need to get off my butt and literally just throw that into my calculator real quick. So I should have that done today. Homework set number 3, probably sometime this weekend. You might get the answers to homework set 4 before you get them to homework set 3, if I'm being honest, because I'm going to work on it and just do it all out in one go.